Welcome to your Chapter 9 lecture. We're probably going to do this lecture in two parts. First part, we're going to focus on geometries and polarity. And part 2 of the lecture, we're going to switch gears a little bit and focus on hybridization and molecular orbitals. So let's get started with geometries. Determining geometries of molecules is entirely concerned with central atoms. Okay, we're really only going to pay attention to what is happening on the central atom of a Lewis structure. Okay, so determining these things starts with a correct Lewis structure. Okay, we must have a correct Lewis structure. So hopefully you are really good at the Lewis structures and you can confidently draw those without difficulty. Okay? Without a correct Lewis structure, you're not going to be able to determine the geometry. Okay? So the second part to this is you're going to determine the number of electron domains. Okay? And when I say domains, I also mean areas of electron. Okay? So the areas, the number of electron areas or electron domains gives what we referred to as the electron geometry. Okay? And the electron geometry is kind of like a base shape. Okay, we're going to put that in parentheses. Okay, and the base shape determines our bond angles. Okay, the electron geometry is what determines the bond angles for our molecule. Okay, now the next part to this is imagine any lone pairs on the central atom. Are invisible. Okay? They're there, but they're invisible. Okay? Now, the whole point of this is that this is based on a thing called Vesper. Okay? So, valence shell electron pair repulsion. And I'll talk about that here in one little second. I'm getting a little ahead of myself. So, with imagining those lone pairs on the central atom being invisible, basically you start with your base shape. And subtract pieces that are invisible. Subtract the invisible parts. Okay? So, Vesper, and it's actually, the acronym is VSEPR, so V-S-E-P-R. And it stands for valence shell electron pair repulsion. Okay, this is Vesper theory. Okay, and the whole point of Vesper theory is that electrons are all negatively charged, and so regions of electrons will push each other away. Electrons repulse each other. Okay, so if your regions of electrons are tied to a central atom, they're going to push each other away so that they can get as far away as possible, right? And the analogy that I often give is kind of like when you're at a holiday gathering with cousins or sisters or brothers that you don't get along with. You often find ways to stay as far away from them as possible, but you can't leave the house, right? Because if you do, then grandma gets mad and Christmas dinner's ruined and things like that. So these regions of electrons that are tied to the central atom will rearrange themselves to find an optimal shape so they can be as far away as possible. Okay, so let's look at our simplest type of things. So my first example, we're going to start with CO2. Okay, and if I draw a correct Lewis structure for CO2, I should end up with something that looks like this. Okay, so what I want to do first is determine how many regions of electrons are around this central atom. Okay, now single, double, triple bonds, they all count for one region. Okay, so what I've got here is, looking at the regions that I have one region here and a second region here. I'm not paying any attention to those lone pairs because they're not the central atom. Okay, so let's not focus on those. Okay, so if I have two regions on my central atom, my electron geometry, I'm going to call this EGO for short, electron geometry, is linear. Okay, those electron areas, those regions of electrons are going to try and get as far away from possible, but they're still tied to the central atom. So the farthest they can get is 180 degrees from each other. So our bond angles are 180 degrees. Okay, when we have two regions of electrons. Okay, the only option that you have with two regions of electrons is a linear molecule. Okay, so let's look at something a little bit more complex. Okay, so I'm getting fancy with some actual some images here. So let's take an example of Bf3. Okay, Boron Trifluoride. Right, and if I draw a correct Lewis structure, I'm going to end up with, if I do it straight Lewis style, I'm going to have something that looks like this. And for sake of brevity, I'm going to not draw all of the lone pairs on the outside atoms because I really don't care about them and it's just time consuming. So there's my first task, draw a correct Lewis structure. My next task is to determine how many regions of electrons there are around the central atom. That's the boron, right? So I'm going to count 1, 2, 3 regions. Okay, so when I've got 3 regions tied to my central atom, what's going to happen is they will push each other away, and if I draw my Lewis structure a little bit more accurately, they're going to get as far away from each other as possible. And what we end up with are bond angles of 120 degrees. So let's draw that here. So between this guy and this guy. Okay, and our molecule's flat. Okay, so we're going to call this, so this makes a triangle, right? Triangular shape, and it's flat, so we call this trigonal planar. Right? Our electron geometry is trigonal planar with bond angles of 120 degrees. Now I don't have any lone pairs, so I'm not going to subtract any pieces. I'm not going to pretend any part of this structure is invisible. Okay? So when your electron geometry has no lone pairs, the electron geometry is the same thing as the molecular geometry. Okay, so electron geometry considers all of the regions of electrons around the central atom. My molecular geometry takes into account any lone pairs on the central atom. Okay, so let's see how that plays out when it's not this way. All right. So our example for this molecule, a good version of things would be the NO2 minus ion. Okay, so if I draw a correct Lewis structure for NO2 minus, I'm going to end up with something that looks like this. Okay? And again, I'm omitting the lone pairs on the outside atoms, right? Just for sake of being complete. On this particular one, I'm going to go ahead and draw them, just so you can see that. Okay? So our correct Lewis structure looks like this. Now I'm going to determine how many areas of electrons there are. Now the lone pairs count as a area. Okay? Lone pairs count. Okay? So the lone pairs count. Double and triple bonds count as one area. Single bonds also count as one area. So I've got 3 regions of electrons. Okay? But I've got one lone pair. Right? So I take my base shape, which we saw our base shape up here. Okay? And then I imagine that one of my pieces, one of the parts of my base shape is invisible. Okay? So what I'm left with is a bent shape. So the molecular geometry is what's left over. So molecular geometry, we refer to that as bent. Okay? Now, we still have approximately 120-degree bond angles. Okay? Now, when I say approximately, it's because the lone pairs push harder. Okay? The lone pair region is a little bit larger than the atom region, and so my lone pairs are pushing down on this, the other two, right? So my things are getting squeezed in the middle, so my bond angle is slightly less than 120 degrees. We're talking about something like maybe 118, like 119, 118, 117, somewhere in that ballpark. We're not precisely sure. It depends on these species. Okay, so we say the bond angles are approximately 120 degrees, but probably slightly less. Okay, so if I were to take my NO2 drawing and draw my Lewis structure in a slightly more Vesper-oriented fashion, I'm going to end up with something that looks like this. Okay. Now, the ability to take your Lewis structure and draw it sort of like your Vesper structure, that's going to be important when we get to molecular polarity of molecules. Okay. So, let's move on to the next step. Right? If I have 4 regions of electrons, right? So an example of something that has 4 regions of electrons, let's look at the ammonium molecule, the ammonium ion. Okay, if I draw a correct Lewis structure for ammonium, we end up with this drawing, right? And then my next step is how many regions of electrons are around the central atom. And we've got 1, 2, 3, and 4. So 4 regions or domains equals tetrahedral. Electron geometry. Okay? If I have a tetrahedral electron geometry, my bond angles are 109.5. Okay? Now, as we progress forward, it's going to become slightly more difficult to draw things in 3 dimensions, but I want to talk about how we can do that on a flat surface real quick. So if I take my ammonium molecule or ion and put it in sort of a 3-dimensional drawing, I'm going to have 2 arms of my structure in the same plane as the page, right? And then if I draw a wedge, that means that that part of the arm is coming out of the page at you. And then if I draw a dash, that means that it's going back into the board away from you. Okay? So, no lone pairs means that my electron geometry, EGO, and GO, is the same thing as my molecular geometry. Okay? And that's just saying that with no lone pairs, there's no part of this molecule that's invisible. Okay? So, next example, if we make something invisible and we have a lone pair. So an example of this might be something like PCl3. Right? If I do a Lewis structure for PCl3, I'll end up with something that looks like this. And just once again, I'm not putting the lone pairs on the outside atoms because I really don't care about them. Okay? They don't play any part in the shape of my molecule. So how many regions do we have? Lone pairs count as one. One region, two regions, 3, and 4. 4 regions. EGO is tetrahedral. Right? So we have approximately 109.5 degree angles, right? But remember, the lone pairs push a little harder on all the arms of this molecule, right? So it'll be slightly less than 109.5. Okay, so we see approximately 109.5, but slightly less. Okay, now, taking a look at what we have here as far as this, this shape, the tetrahedral shape, let's take another look at it in its whole, all right? So essentially you have like a tripod with these 3 and then with an antenna, right? So if I take away the antenna, I'm left with the tripod, right? So it's basically a triangular shape at the base, but it's raised up, so it's a bit of a pyramid. So that's why we call the molecular geometry trigonal, as in triangle, trigonal, pyramidal, or pyramidal, depending on who you talk to. Okay? So trigonal pyramidal is the molecular geometry. My electron geometry, which decides my bond angles, is tetrahedral because I have 4 regions around my central atom. Right? Let's see if we take another one away. All right? So 2 lone pairs with 4 regions. Examples of that are H2O. Let's change colors. Or a more interesting example is SF2, right? It's really easy to do a lot of examples with hydrogen, but let's do the SF2. If I do a correct Lewis structure for SF2, I'm going to draw this, right? With lone pairs around my fluorines, which is tedious to draw, right? So there's our correct Lewis structure. I have 4 regions around my central atom because the lone pairs each count as a region. 1, 2, 3, and 4. Okay? So 4 regions makes us tetrahedral. Tetrahedral electron geometry. So approximately 109.5. Okay, but slightly less, okay, because those extra lone pairs are pushing down harder on the parts that are still visible, okay? Now, if I take my antenna away from my tripod and one of the legs away from the tripod, our molecular geometry, what we're left with is bent, okay? Now, I want to make you aware, right? So we've seen a bent geometry before when we were looking at trigonal planar. And I'm going to scroll up so don't get seasick. Right? So when we were talking about bent geometry from a trigonal planar, we had something closer to 120-degree bond angles. Okay? But when I have a bent geometry that comes from tetrahedral, we have approximately 109.5-degree bond angles. Okay? So this one's going to be bent a little bit sharper than the bent shape that comes from trigonal planar. Okay? So, but the takeaway from all of this is we start with a base shape. That's your electron geometry. And then for every lone pair you have, just imagine that a piece of that geometry is invisible. And then whatever you're left with what you can see, is your molecular geometry. Okay? So let's up the ante a little bit more. Let's go with 5 regions of electrons. So now we're getting into species that are breaking the octet rule. Right? Remember, anything in period 3 or lower, the third row of the periodic table, is capable of breaking the octet rule. We also can refer to this as something having an expanded octet. Okay, so 5 regions. Let's take a look at an example where we have 5 regions of electrons. So a good example of that is PCl5. Phosphorus Pentachloride. I hope you're remembering your nomenclature. It's going to come back to you on the final. Heads up on that. All right, so if I draw a correct Lewis structure for phosphorus pentachloride, I'm going to draw something that looks like this. With all the chlorines having 6 lone pairs around them to complete their octets, right? So with this, I now have 2 different sets of bond angles, okay? So around the middle, right? So we can think of this as sort of like a little space station, right? Like it's got a platform and then a rod running through the middle of it. So around the middle, we refer to these parts as the equatorial atoms. Okay? And you can think about that equatorial sort of like the equator of the Earth is like a band that runs around the middle of the Earth, right? So these ones that go around the center of this molecule, we refer to those as the axial atoms. Now the ones that run through the middle, stop. These ones that run through the middle, we refer to these as axial. Okay? And you can think of that like an axis or an axle of a wheel or anything of that nature to help you remember that. Okay, but we have 2 sets of things. So looking at these 2 sets, I've got 2 different sets of bond angles. So between the axial and equatorial, we have 90-degree bond angles. Okay, and then between the different equatorial atoms, we've got 120-degree bond angles. Okay, so this thing around the equatorial makes a triangle, right? And then from equatorial to axial, I have a pyramid, right? But I also have a pyramid on the bottom as well, don't I? Right? So that's why we call this trigonal, for that triangle shape around the equatorial, bipyramidal, so bipyramid, 2 pyramids. Okay? So if I have no lone pairs, my electron geometry, EGO, is trigonal bipyramid, trigonal bipyramidal, and my molecular, because there's no lone pairs, no part of this drawing is invisible, is the same thing as my electron geometry. All right. So, as we've done with the previous set, let's see what happens when we have a lone pair. All right. So an example of this one, let's take a look at if I were to draw a correct Lewis structure for Sf4. Okay. That Lewis structure would look like this. With two lone pairs on my central atom. Or excuse me, a lone pair, two electrons. Okay, so I've drawn a correct Lewis structure for Sf4. Let's determine how many regions of electrons there are, or domains of electrons there are. I've got one for the lone pair, 2, 3, 4, 5. Okay, so 5 regions, or areas, or domains. My electron geometry is trigonal bipyramid. Bipyramidal. I should say pyramidal every time because that's what mastering is going to ask for and all that stuff. So, okay. Now, we have a lone pair. So, the important thing to remember to realize with this drawing, because I have two different types of atoms here, I have axial and I have equatorial, right? When I start to decide where to make things invisible, the equatorial is where it's going to be, right? Because equatorial has 120-degree bond angles, right? Right? So there's more space around the equatorial than there is at the axial. So I'm going to give all of my electrons the greatest ability to get away from each other, and I'm going to pull from the equatorial first. Okay? So what we're left with is a very technical term for this molecular geometry, and that's seesaw. Okay? And the reason that I've rotated this, so all I've done is rotated 90 degrees, so that you can more easily see how they would get the idea of a seesaw. So that's what you have. So we still have both sets of bond angles. We still have 120 degrees here, and we still have 90 degrees between axial and equatorial. Okay, so one lone pair, we have seesaw molecular geometry. Right? So let's go ahead and take away another for lone pair. Okay, so 5 regions, 2 lone pairs, right? An example of this one would be Cl, let's go back to blue, stay consistent, would be ClF3, right? If I draw a correct Lewis structure for ClF3, chlorine trifluoride, we're going to end up with something that looks like this, right? Count our domains or our regions of electrons. We've got 1, 2, 3, 4, 5. Right? So 5 domains. Okay? Domains or regions or areas, right? I'm trying to remember to use the term domain because it's the word that the textbook uses in the tables that show these geometries. Okay, 5 domains gives us a electron geometry of trigonal bipyramid, trigonal bipyramidal. Right? So we still have, and that's going to dictate our bond angles, right? So our electron geometry has 90 and 120. But now with two lone pairs, right, I take another one off of the equatorial, right? When we imagine parts are, that should be a Q. Imagine that parts are invisible. We're taking off of the equatorial atoms first, okay? As a matter of fact, we really never take them off of the axial. They only come off of the equatorial, right? And I've rotated this 90 degrees to the drawing on the right, and what we're left with is a very technical thing called T-shape. T-shaped molecular geometry, right? And with a T, all we have left are 90-degree angles. Okay? Because we've removed all the other pieces that would make 120-degree bond angles. Right? So, and I've left these typed regions up here at the top, sort of as like a synopsis. Okay. All right, let's take another one off. Right? So an example of this type of molecule would be Xenon difluoride, which actually does exist. They have to make it in a laboratory, but it does exist. So if I draw a correct Lewis structure for xenon difluoride, we get xenon in the middle, and we end up with 3 sets of lone pairs around our central atom. Right. So I have each lone pair counts as one domain. 1, 2, 3, 4, 5. And so 5 domains means that we are still trigonal bipyramidal for our electron geometry. Okay? But take a look, if I take all of my axial away, or excuse me, all of the equatorial away, right? These are all the equatorials. What am I left with? A linear molecule. And it is, with linear, we've got 180-degree bond angles. Okay. That's the only thing that linear can be. All right, you ready for the Big Daddy? Here we go. 6 regions of electrons. Okay, this one is called octahedral. Right, now, you may be thinking to yourself, as I did when I was in your seats, octa means 8. So why does 6 regions give us something called octahedral? And the reason for that is if you connect all of these points and cover them with planes, right? These ones too. What you end up with is an octahedral shape. Okay? That's why they call it octahedral. Okay? So with octahedral, all we have are all we have are 90-degree bond angles. Okay, they're all evenly spaced around each other. Right? And we can look at this and think that we have axial and equatorial, but if I flip it over, everything's still the same. Okay? So an example of an octahedral molecule would be one of my favorites, Sf6 Sulfur Hexafluoride. Right? And if I draw a correct Lewis structure for this one, going to look something like this. Right, with electrons around all of the fluorines. So sticking with our pattern, I'm going to determine how many regions of electrons, and I'm going to count 1, 2, 3, 4, 5, 6. So 6 domains is octahedral geometry. Octahedral electron geometry. Okay, 90-degree bond angles with no lone pairs. My electron geometry is the same as my molecular geometry. Okay, because none of the parts are invisible. And so let's see what happens if we take one off for a lone pair. All right, and it really doesn't matter where I pull from because all of my bond angles are the same. So it doesn't matter. I'm just going to pull one off sort of arbitrarily from the bottom, right? Because this is going to make it easy to look at. Right, so an example of this particular molecule is Bromine Pentafluoride, Bf3. Okay, so if I look at this guy and draw a correct Lewis structure for it, I'm going to draw something that looks like this. Right? We're going to count the domains. So the lone pairs count as a domain. So 1, 2, 3, 4, 5, 6. So 6 domains means that we have octahedral electron geometry. Okay? So we still have 90-degree bond angles. Right? Now, with one lone pair missing, what I'm left with is a square, right? And a pyramid, right? Okay, so with one lone pair, we have square pyramidal. Molecular geometry. Okay. So now remembering that those lone pairs down there are pushing a little extra hard, so our bond angles are slightly less than 90 degrees. Okay, but still approximately. Now if I take another one off, I'm going to basically pull off the top of the pyramid this time, right? Because my goal is to make sure that my electron regions have as much room as possible to spread out. Okay, and in this case, a flat square is the way to go. So an example of this molecule would be Xenon Tetrachloride. So if I take and draw a correct Lewis structure for Xenon Tetrachloride, I'm going to end up with something that looks essentially like this. Okay. So sticking to our strategy, how do I tell first what is the electron geometry? I'm going to count the regions. I've got 1, 2, 3, 4, 5, 6 regions, or 6 domains. Means octahedral electron geometry. Okay, and then if I imagine that 2 pieces of that electron geometry are missing, say the top and the bottom, what I'm left with is a flat square. Okay, I realize that looks a bit more like a rectangle or a, what do you call it? I'm blanking on my names of shapes, but what we're left with is a square which is flat, so square planar. Molecular geometry. Right? With 90-degree bond angles. Okay? In this case, they are 90 degrees because the electrons on top and the electrons on bottom are pushing equally, so we're not squeezing anything out of shape, right? They're sort of balancing each other out. Right? So there's a definite system to this process. All right. So now that we've gone over all the shapes, you can find these geometries in your book. Tables of geometries. They are on pages 344 and 45 and 348. Okay? So now, moving on. So, one of the reasons that we care about geometry is that shape matters to polarity. Okay? So, we haven't really spent much time talking about polarity yet, but to visit the topic, so if I have a molecule of hydrofluoric acid, okay, simple HF, right, and I know that fluorine is the most electronegative atom on the table, right, and if I look up its electronegativity value, I have a value of 4, and hydrogen has a value of 2.1, okay, and I can tell that whether I look up the numbers or not. I know that fluorine is going to be more electronegative than anybody, okay? So when determining whether or not this is a polar bond, we look at who's more electronegative. Fluorine is more electronegative. Okay, so that means that the electrons are going to spend more time in this direction. Okay, and we draw an arrow because it shows the direction of the electrons. Okay, and that also means that this is the negative end of this bond, and this is the positive end of this bond. Okay, and the reason that we have the little crosshatch on the arrow is because that shows the positive end of things. Okay, so if I sort of draw a map of what the electron cloud looks like, right? Most of the electrons are going to spend their time around the fluorine, so my electron cloud is going to sort of look like this, right? With the negative end and the positive end. Okay, so this is referred to as a polar bond. Okay, because I have a difference in electronegativity. Okay, so if there's no difference in electronegativity, or if it's too small, so for example a carbon-hydrogen bond, the difference is very small. It's too small to matter. So this is basically a nonpolar bond. Okay? So when I'm looking at whole molecules instead of individual bonds, this is where things get a little bit more complicated. So let's revisit our old friend NO2-. Okay, let's look at that molecule. And if I draw it sort of with its shape in mind, so if I draw a basic Lewis structure, I'm going to end up with something that looks like this, right? And then if I take it into account the fact that it's bent, because I have 3 regions with 1 lone pair, bent molecular shape, I'm going to end up with a drawing that looks like this, right? Now, nitrogen is less electronegative than oxygen, right? So oxygen is going to pull the electrons toward it, right? Both of these oxygens are going to pull. So if I look at each of these bonds, I'm going to draw vectors that show the direction that the electrons are going. Okay? Now they're not pulling directly away from each other because I have a bent molecule, right? The shape is important. So if I were to draw sort of a net pull for this in the direction of where the electrons are going, let's use green instead, right? Overall, I have a net direction that is pulling down, okay? I have a net pull in the downward direction, okay, because of the direction the vectors are going, okay? If I have a net pull, that means I have a polar molecule. Okay, so the shape is important. Shape is important. Okay, because I can have polar bonds and still end up with a non-polar molecule. Let's take a look at how that plays out. Right. Let's take a look at CO2. Right, if I draw a correct Lewis structure for CO2, we look like this, and we see that it has two regions of electrons, so it's linear, right? So 180-degree bond angles. So this actually shows the molecular shape. So linear molecular shape, right? Now oxygen is more electronegative than carbon, so I'm going to draw a vector that shows the direction that the electrons are going. Right? Now, the two bonds are pulling directly away from each other. And they're pulling with equal strength. Right? It's kind of like a tug of war between two equally powerful teams. Right? So they're pulling directly away, so they cancel each other out. Cancel out. Right? So I have no net pull. No net direction of electronegativity. No net pull. The vectors cancel each other out, so I have a non-polar molecule. Okay? Even though I have polar bonds, the shape dictates how this plays out. Right? So because of the shape, those two vectors are canceling each other out. I have no net pull, means a non-polar molecule. All right, let's look at a couple other examples. Let's look at NH3. Right? If I draw my ammonia molecule with its actual geometry in mind, so let's draw the simple Lewis structure first, just to be in the practice of determining correct geometry. So my molecular geometry, molecular geo, is trigonal pyramidal. Right? Starts with a tetrahedral shape, and then I take away the antenna. So if I draw it sort of with its geometry in mind, it's going to look like a little tripod or a little pyramid, right? Now, nitrogen is more electronegative. Right, I'm going to zoom in just a little bit. Nitrogen is more electronegative than hydrogen, so my vectors are going to be going up towards the nitrogen, right? But I don't have anything pulling back down. I don't have anything canceling out those vectors. Generally in an upward direction. right? So I have a net dipole equals a polar molecule. Okay. Now, let's see what happens if I look at the ammonium ion. Right? If I draw a basic Lewis structure for ammonium ion, right, we're going to end up with something like this. 4 regions, no lone pairs, so I have tetrahedral molecular geometry. Right? So we sort of redraw this a little bit to take into account its actual shape. Okay? Now, if I think about this thing in 3 dimensions, right? I have the vector pulling down this way, a vector pulling up this way, and this way, right? So these vectors cancel each other out. Even though I have polar bonds, if the vectors cancel out, I have a non-polar molecule. Okay, and that's usually the situation when I have something where all of the outside atoms are the same, and I have a symmetrical structure. I'm going to end up with something that's nonpolar. All right, let's look at a slightly more complex molecule. Let's come back to our friend Br(F5). Right, if we draw our Lewis structure for Br(F5), we'll have some lone pairs, a lone pair on the bromine. So 6 regions of electrons, so we have an octahedral electron geometry, 1 lone pair on the central atom, so our molecular shape is square pyramid, square pyramidal. Okay, so now let's sort of zoom in here, right? And I'm gonna sort of fix this to reflect, because it's sort of already mildly in a correct version. Okay. So fluorine is more electronegative than bromine. So all of these bonds, the electrons are getting pulled towards the fluorine equally. Right? So around the base of the pyramid, things cancel out. The pyramid base, everything cancels, right? Because they're pulling equally in all 4 directions at the base of the pyramid. But I have the top of the pyramid here pulling up with nothing else pulling down. So I have a net pull in this direction, right? Because there's nothing down here pulling back down to cancel out that pull that's going up. So I have a polar molecule. Okay. All right. Now let's take a look at, so now that we're wizards with polarity, let's look at how the Vesper model works with larger molecules instead of just these simple ones with 1 central atom. Let's look at something that's bigger, that has more than 1 central atom. So let's take a look at a molecule that looks like this. Carbon, bonded to a nitrogen, double bonded to another carbon, which is bonded to an oxygen, with some lone pairs on it, and we have some lone pairs on the nitrogen. Okay? So what we want to do is work on one central atom at a time. Okay? So let's take a look at the left-hand carbon, right? So I'm going to take and sort of highlight it in yellow here. Right, and look at that carbon right there. So we're focusing on this guy, right? So if I sort of bring that out and take a look at it down below, I've got a carbon, hydrogen, 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 the bond that eventually goes to a nitrogen, right? There are 1, 2, 3, 4 regions. Tetrahedral. Okay, 109.5 degree bond angles. Right? And it has a molecular shape of tetrahedral because there's no lone pairs. Okay, so just evaluate each atom in turn. So let's take a look at now what's going on with the nitrogen. All right. So the nitrogen up here is got a situation like this. So the nitrogen eventually gets connected to a carbon over here. It's got a double bond over here which connects to a carbon, and I've got 2 lone pairs on it. Or a lone pair, excuse me, 2 electrons, a lone pair. And we use the same tactic for evaluating it. We've got 1, 2, 3 regions. So it has a trigonal pyramidal, or no, it should be trigonal planar. Sorry. Trigonal planar electron geometry, EGO. So we've got 120 degree bond angles, approximately. And then we've got 1 lone pair. So our molecular geometry, our shape, is bent. Okay, and then our next atom is the other carbon, the carbon on the right. And let's sort of pull it out, and we'll say that that carbon is double bonded, eventually becoming to a nitrogen, and then double bonded to an oxygen. Right? So I have 1, 2 regions. So it's linear. 180 degree bond angles. Okay? So if I wanted to, I could take and draw this molecule in a slightly more correct way that takes into account its geometries. So when I do that, I'm going to end up with something that looks like I have an overall sort of bent shape to this molecule. Okay? Because the left-hand carbon, that's tetrahedral. The nitrogen is bent. And the right-hand carbon is linear. Okay, so we can evaluate shapes of larger molecules just based on the individual geometries. Okay, we're going to stop there with this particular video. I'm going to get it posted and let you all know that it's posted. And we will come back with our next bonding theories, our next two bonding theories, which are valence bond theory